Howdy students. In the last video, we talked about the carbon budget and how much carbon dioxide we can emit and stay below the warming levels that the world has judged as dangerous. As we talked about in the last video, humans can only emit about 158 gigatons to the atmosphere to have a chance to stay below the 1.5 degree threshold. This plot shows the emissions per year required to reach that 1.5 degree target. We are here. So we need to start rapidly reducing emissions starting now. Emissions need to decline about 45% below 2010 levels by 2030. This is going to be extremely challenging. These cuts are unlikely to come from poor developing countries that are trying to raise their citizens' standard of living. So the majority of these cuts are going to come from the rich world. After these deep initial cuts, emissions need to reach net zero by 2050. And after that, emissions actually need to go negative. Negative emissions mean that humans are removing more carbon dioxide from the atmosphere than they're adding. Our ability to do this at this scale is entirely speculative. This scenario requires removing something like 100 gigatons, that's 100 billion tons of carbon dioxide over a few decades. This is a Herculean industrial task, to put it mildly. If you think about how much infrastructure and money it takes for us to emit carbon to the atmosphere, think about all the wells, mines, trains full of coal, pipelines, refineries, trucks, power plants. It seems likely that it's going to take a comparable amount of infrastructure to pull carbon out of the atmosphere. This will be difficult, but if we can do this, we could keep warming below 1.5 degrees Celsius. But we have another option. We can let the temperature exceed the 1.5 degree limit for a few decades. This temporary excess in temperature is what's known as an overshoot. If we look at the emissions trajectory associated with this overshooting 1.5 degree limit, we can see that it has slower near-term cuts. This reduces the cost of achieving the policy goal. To understand this, imagine you build a coal-fired power plant. This is a huge upfront cost, and it pays for itself over many years. If it takes 30 years to pay for itself, then it is only profitable if the plant operates for much longer than that. If you tear the plant down after 25 years, the owner of the plant and our economy loses money. So the cheapest way to achieve any emissions reduction is to let infrastructure wear out naturally, and when you replace it with climate-safe technology. In this example, you would wait until the coal-fired plant has reached the end of its life, and then when it's replaced, you make sure it's replaced with solar or wind. Scrapping the power plant when it has useful life left is much more costly to our economy. So this overshoot emissions trajectory with slower near-term cuts allows more equipment to be replaced on schedule instead of scrapped prematurely. That minimizes near-term costs, but there's a flip side. Remember from the last video that we have a set carbon budget that we cannot exceed. More emissions in the near term requires bigger carbon removal in the second half of this century. The scale of this removal is even more daunting than in the scenario with no overshoot. We'll need to remove hundreds of billions of tons of carbon in a few decades. You might be asking yourself how we remove carbon from the atmosphere. One option is to build an industrial plant that sucks in air, removes the carbon dioxide from it, and then releases the carbon-free air back to the atmosphere. The captured carbon is then sequestered in some kind of long-term reservoir, like injecting it deep underground into a depleted oil and gas field. You can think of such a plant as effectively an artificial tree. This process is known as direct air capture. Another option is to use photosynthesis to our advantage through something called bioenergy with carbon capture and storage. usually referred to by its acronym, BECCS. In this process, carbon is pulled from the atmosphere when plants grow through photosynthesis. The plant matter is then burned and energy is produced. But instead of venting the carbon produced in combustion back into the atmosphere, the carbon is captured and it is sequestered in the same kind of long-term reservoir discussed above. Doing this leads to a net decrease in atmospheric carbon. Whatever is chosen, the technology must be cheap, scalable, meaning that you can build enough of it that you can remove billions of tons of carbon every year, and have acceptable side effects. For example, BECCS is cheap and scalable, but the necessity to grow large amounts of crops could have serious side effects, such as leading to destruction of forests or displacement of food production. Direct air capture is low impact and potentially scalable, but presently expensive. So what's the upshot? Stabilizing at 1.5 degrees is going to be really, really hard, even if we allow overshoots. It will require deep, near-term cuts beginning within a few years. It will also require large amounts of carbon to be removed from the atmosphere in the second half of this century. In addition, as you saw in Chapter 6, other greenhouse gases make important contributions to climate change. Reducing emissions of non-carbon dioxide greenhouse gases offer cheap and fast ways to reduce radiative forcing, and these must be pursued. Most importantly, however, is that meeting this goal requires political will. Looking around the world right now, it's hard to see enough of it to be optimistic we'll start deep cuts in emissions in the very near future. Now, let's talk briefly about the weaker 2 degrees Celsius target. This shows a trajectory for 2 degrees, along with the 1.5 degree trajectory with no overshoot. As you can see, this 2 degree target also has near immediate cuts. However, the rate of emissions reduction is quite a bit slower than for the 1.5 degree target, owing to the larger carbon budget available for 2 degrees. For this scenario, emissions reach zero late in the 21st century, and there are small negative emissions thereafter. Note, though, that other trajectories are possible. Like we did with the 1.5 degree target, we could trade off early cuts for negative emissions later, so alternative 2 degree trajectories could have slower near-term reductions, but then have larger negative emissions in the second half of this century. So what's the upshot? Stabilizing at 2 degrees is easier than the 1.5 degree target, but it is still going to be a challenge, and we will experience larger and more costly climate impacts. However, it is my opinion that this target is far more practical than the 1.5 degree target. But to reach even the 2 degree target, we need to get serious about climate change, which the world in general, and especially in the US, is not. Whatever the target we decide to aim for, there's a trade-off between strong action now and later. If near-term cuts are weak, then we'll need either faster cuts later in the century or large carbon removal to stay below 2 degrees. It's amazing to realize that we've known about this problem for many decades. Had we taken action in the 1990s, when the details of the problem were crystal clear, the effort required to reach one of these targets would have been much, much less than required today. But we didn't, and now it's the metaphorical last minute and we're facing down the barrel of the gun. If we keep dithering for a decade or two, we will miss the opportunity for either target and commit ourselves to much larger and more costly climate change. And now, your moment of dog.